Hi everybody, I'm Julie Powell and I'm product manager for the ArcGIS API for JavaScript and now our new design system.
Hi guys, I'm Matt and I work on the rendering engine for the JavaScript API.
Hi, my name is René Unruh. I'm joining you from Vienna, Austria, and I'm a software developer with the real-time and big data team. In this session, we will demonstrate how various types of data can be fed into your application in real time from ArcGIS Velocity, GeoEvent Server, or your own custom WebSocket implementation. Then, we will demonstrate how these feeds can be utilized in web apps using the ArcGIS API for JavaScript for real-time visualization and analytics. As we all know, the world is increasingly connected, way beyond computer systems and phones, now down to devices and sensors that are very diverse. Soon, there are going to be over 20 billion connected things in the world. And while many of these are consumer-focused, there's also a huge growth for devices that support industry and business applications. It is also estimated that roughly 80% of sensor data has a location component, which means there's a growing variety of geospatial use cases in the Internet of Things. Businesses of all types want to monitor, manage, and optimize their assets, whether that means managing a fleet of vehicles or allocating and tracking valuable hospital equipment. Many organizations want to leverage contextual information to protect critical infrastructure by detecting, locating, and isolating areas at risk and responding in near real time. This list really goes on and on. In order to meet the demands of any of these use cases, software usually needs to have one or more fundamental real-time capabilities. The first is the ability to ingest real-time data. Real-time data comes from many sources, from an increasingly diverse array of systems, devices and sensors, IoT platforms, mobile device apps, third-party servers, and so on. After ingestion into the software system, effective visualization is critical. For some use cases, the need is to have immediate fluid visualization as soon as data arrives. In other cases, drawing data on a repeated basis from a data source will show new information in what we call near real time. The two other real-time capabilities are analytics and alerting, or more broadly, taking action. As you can see, there are many products in the ArcGIS platform that have real-time capabilities in one or more of these areas. Looking across all four of these fundamental pieces, however, ingestion, visualization, analysis, and alerting, the comprehensive solution for real-time in ArcGIS is provided with GeoEvent Server or ArcGIS Velocity. They provide out-of-the-box diverse connectors for talking to different industry systems, parsing data in various formats, and turning it into ArcGIS features. Both products drive real-time visualizations with the stream layer and include alerting through email and text messages. GeoEvent and ArcGIS Velocity perform fully real-time continuous analysis on data as it arrives. The capabilities of GeoEvent and ArcGIS Velocity are agnostic, as opposed to being industry-focused. They can be configured to enable any real-time or tracking workflow for vector data. In many ways, these products have comparable functionality and are just different deployment options. GeoEvent Server is your traditional software product. It is installed as part of ArcGIS Enterprise in your infrastructure. In contrast, ArcGIS Velocity is a capability of ArcGIS Online. It provides many of the same capabilities as GeoEvent Server in a platform that is fully managed by Esri, and because of that, it doesn't need a GIS admin to manage it. Whereas GeoEvent Server should be considered an advanced admin-level product, particularly in terms of the necessary GIS and IT controls to support access to external feeds or different secure data streams. However, because GeoEvent Server is something that can be installed offline or in a closed environment and is fully extensible to expand its functionality beyond the core product, that is something a lot of customers need. ArcGIS Velocity runs in a secure but public cloud infrastructure, so it supports feeds available over the internet, and because the architecture is designed from the ground up to be cloud native. It can product far greater scalability and resilience over traditional software options, supporting higher velocities and volumes of data than what is available with GeoEvent Server. Both products have full end-to-end control, providing solutions for your real-time visualization and analytic needs. It just comes down to what other deployment requirements you might need to consider. If you want to learn more about any of these products, I highly recommend attending these 2 live sessions today and tomorrow. They will walk you through how you can connect to virtually any type of streaming data, perform real-time analytics and processing on the streaming data, as well as automatically disseminate information and alert personnel when specific conditions occur. In this session here, we're focusing on effective visualizations of real-time data. We will look at the capabilities you as a developer can use through the ArcGIS JavaScript API. And to get started, I will hand it over to Julie.
Thanks, Renee. All right, let's talk about visualization of real-time data in the JavaScript API. I first want to start by just spending a couple minutes on polling versus pushing and how important it is to really understand how frequently your data is changing. Is it every second? Is it every 5 minutes? And also, how quickly do you want to visualize those changes once they're available? The different options you have in the API is either using a refresh interval, and you're simply telling the layer, how frequently should it check for updates? Is it 1 minute, 5 minutes, 30 seconds? Versus if you want to take a push approach, using a WebSocket, and that's where as soon as there's data available or updates on the server, it's pushed to the client and then it can be visualized right away. If you want to use that approach, you'll be using the API stream layer. And that's really where we're going to be focusing our talk today. So how does the stream layer work? Well, first of all, you're going to get updates via a stream service. It's going to send the observations with attribute updates, geometry updates, and that's pushed through the WebSocket, and then it's displayed in the app via the stream layer. And that stream service could be coming from a GeoEvent server, as Renee was talking about, ArcGIS Velocity, or a new type, which is a custom stream service that Matt will be talking about later. So some of the basics, these are the cliff notes about the stream layer. First of all, you can display this data in both 2D and 3D. There's track awareness. So if you have, say, a moving object and multiple observations are sent for that same object, basically it's tracked using a track ID. So we know to display just the amount of observations you want for that individual object. You can also define a renderer. So if you want to display, say, a plane and the size of the plane based on the altitude, you can use visual variables and use all of the rendering capabilities in the API to display that data on the map. We also have purge options. So how do you want to manage stale features? You can set the max observation. So that's in the case of the track awareness. So if you have an object moving, how many older observations do you want to display on the map before you remove it from the map? Or you can display, you could configure the max age of features. So just how long should a feature remain on the map before it's essentially invalid and you want to remove it? Or you can control the max number of features. So maybe you just want to display 10,000 features on the map at once. A very important aspect of stream layers is you have all of the client-side capabilities as you do with other layers. So as you're learning about these different things you can do in the API in different sessions, you can also apply that to the stream layer. Because essentially, once that data is on the client, you have all the rendering, client-side querying and filtering and statistics, all of those things you have available now with the stream layer. So now I'm going to demonstrate some of the basics about stream layers and then show you some of the cool ways that you can visualize and interact with them. For this first demo, we're going to look at flights in the United States. So I've just added a stream layer, and you can see the airplane showing up as the data is pushed to the client. So let's look at the code of how this part works. So first, I'm just creating a new stream layer. I'm setting it to the URL to that stream service. I'm saying that I want, after 10,000 airplanes, I want to start deleting the older ones. And then I'm defining a renderer. If I didn't define a renderer, it'd simply show up with blue dots. But in this case, I'm using SVG picture marker symbol. And then I'm driving the rotation by the heading attribute in the stream service. And then also changing the size of the airplane based on the altitude, and then setting some stops. So it's going to basically do a continuous size variation between those two stops. So the next thing that I can do is I can apply a spatial filter. So this is different than traditional filtering. What is happening here is I'll just set it in this extent, and then as I zoom out, you still see the planes that are outside of this filter. They just essentially have like a grayscale and opacity set on them so that I can emphasize the planes that are within my area of interest and de-emphasize the planes that are outside of this area of interest. And again, this is not unique to stream layers. This is something you can do in feature layers as well to basically have that effect of emphasizing and de-emphasizing based on a filter condition. And that condition can be based on attributes or it could be based on geometry. So to do that, we look down here in the code. Essentially here, I'm setting up the filter to be the geometry of the current extent, and then expanding it, or actually making it a little smaller, and then setting the excluded effect to grayscale and a little bit of opacity. I also could have defined an included effect, which would have applied something to the airplanes within my area of interest. So the next thing I might want to do is filter it based on altitude. So while the filter and effect that I just showed is based on geometry, this one's going to be based on attributes. So here I can say, only show the airplanes that are 10,000 feet or higher, or again, lower than 3,000 feet. And so if you look here, these are actually removing airplanes from the map. So you see, you don't actually see at all the airplanes that are not meeting that criteria. It's actually doing a true filter. So the way that that is implemented is I'm simply setting a where clause on the stream layer view. It's important to note that both this filter and then also the effect that I'm applying, it's on the layer view, meaning that it's all happening client side. I'm not putting any sort of condition to the service itself. It's all just determined client side. And this is possible because there's a full client-side spatial database that's running in the client. So any SQL statement that I could have sent to the server, I could apply it on the client, as well as any geometric operation. Now this demo is very similar to the previous demo, only now we're going to be looking at it in 3D and also with imagery. So I'm going to go ahead and add that stream layer. And one thing you'll notice is these planes are above the ground, and they're actually displayed at the correct altitude relative to the ground. And that works because there's actually a Z value in the stream service itself. The other thing is now I'm not using that simple SVG symbol. I'm using a realistic symbol that I can use for 3D. That's called web style symbol 3D. And it actually displays correctly in the legend too. So the legend just automatically gets the information from the layer and it displays correctly the way that it's configured unless I override it somehow. So I can go ahead and set an attribute filter on the map. Right now it's 10,000 feet or higher. I could do the lower than 3,000 feet. You just see the smaller planes. And one thing you'll notice is that I'm not doing the filter and effect. That's where I was emphasizing and de-emphasizing symbols. That is not yet available in 3D. So the way that you can get a symbol that's like this, that looks realistic, is by using the web style symbol class, as I mentioned. In this case, I just see the name, which is the airplane small passenger. There's other airplanes to choose from, and this type of style. So that's really that, and also setting the, rather than using a map view, using a scene view, you can quickly get the stream layer to display in 3D. Now, if you'd like to explore some of the other symbols you can choose from, you go to the guide, data visualization, and then here you have the web style symbols for 2D, and then you have them for 3D. And I can simply search for airplane, and I see the different airplanes I can choose from, click on it, and then this is how you access it from your application. So it is pretty simple to bring in these realistic symbols into your app. Now, in my previous examples, we were looking at flights, so of course the features were moving. But that may not always be the case. You might have features that stay in one place, but then their attributes are updating. So in this case, I'm looking at Charlotte bike station rentals. And what I've done is added a pop-up. So I can click on one of those and I can see at this station, there's 6 bikes currently available and then 5 empty spots where I can return a bike. So the way you set up a pop-up for a stream layer is the same as other layer types. You define a pop-up template, and then you can use all the flexibility of a pop-up as you want, adding media or like a chart, setting the content simply with this HTML like I did, and then pulling out the attribute values from that feature. Now, this is interesting as it is because I can explore the data, see how it's changing, but something that might be even more interesting is driving the actual symbol layers to reflect the status of those changing attributes. So what I've done in this application is use symbology to indicate the status and some values of the attributes. So here at the bike station, I'm representing the number of bikes available by the number of green lines. And each line represents 2 bikes available. So if I click on that, I see there's 2 bikes available to rent. So I can easily just look at the map and understand what's available at any given point in time. So the way this is implemented is, again, just defining the stream layer and the pop-up template. And then the renderer is using a sim symbol type, which is the ArcGIS cartographic information model. These are vector symbols. But it's doing something special. It's using a custom sim symbol, and I'm going to show you in a minute how you can define that so that this is all custom of how I've put that symbol together and all the different layers. And then I'm also driving how these little lines are put together using primitive overrides. So what's happening is in this expression, it's using an arcade expression to determine how many lines should be displayed based on the number of bikes available. So if you want to learn more about how you can do some of this more advanced and interesting vector symbology, let me show you a few resources. So back in our online documentation, if you go to data visualization and then the last option in there is sim symbol builder. This is a nice little tool that we recently made available. And what you can do is basically add a symbol layer. So pick from all the ones that are available, like icons, pick something you like, and then you can go and edit individual aspects of that symbol and customize it however you'd like. So that up, I can change the color, I can change the outline, and then after I'm done, get the simple JSON that I can use in my application. So it's pretty handy. So this just gives you the static vector symbol. But if you want to drive individual symbol layers based on some logic, what you'll want to do is go to the samples and search for Werman's dots. That's this one that we're looking at here. And this is the sample that shows how you can use those primitive overrides to update individual symbol layers. So it explains how it's done. This is a mapping style from the 1960s. And then it articulates how arcade is used to drive the inner size of the circle and the forest ratio. And the outer size of the circle as well. So this is a good way to learn how this all works. And it's pretty powerful once you understand how these are put together. Okay, so those are some simple examples of how you can use the stream layer to visualize your real-time data, how you can use symbology to represent the status and different visualization techniques, and even doing some client-side filtering. So now I'd like to hand it back to Renee, who's going to talk about some more examples of visualizing using the stream layer.
Thanks, Julie. I will now show you 3 demos that I built, and each of these demos uses different real-time capabilities of the JS API. In my first example, we will look at the security scenario where I'm tracking moving assets and calculating the distance to stationary features by using the geometry engine. The second sample focuses on 2D visualizations. By using a custom layer view, I will show you how you can extend the built-in renderers for real-time data requirements, such as animations. And in my last example, I will show you a prototype that uses an external rendering engine to animate real-time observations with the JS API in 3D. For this demo scenario, I want my map to visually indicate if planes over Germany are getting close to nuclear power plant sites in real time. So my first layer here is a feature layer that shows the stationary locations of these sites on the map. Second, I added a stream layer from ArcGIS Velocity that gives me the real-time positions of airplanes over Germany, here visualized as orange firefly symbols. And as you can see, these points are getting updated every few seconds. With these two data sources, I could already do a lot of analysis on the server side, but also trigger notifications, for example, by configuring a pipeline of events with ArcGIS Velocity. However, for this demo, I might only want to show this information on a small map that is embedded into a dashboard, for example. And therefore, I decided to use the geometry engine and the client-side query capabilities of the JS API to calculate buffers around the planes on the fly here in the client. And I'm using the resulting buffer geometries to create a cert layer that gets continuously updated whenever we receive new data. As you can see, I'm also changing the symbol color of my buffer polygons based on if there is a nuclear power plant within the radius of 50 kilometers from my plane. I also want to show the actual distance between the plane and the power plant on my map, in case the plant gets within the radius of 50 kilometers. So I created another layer here that draws a line between both features, but also has a label that includes the distance. As you can see, we have a few components and layers here that need to be continuously updated. Some of these layers include data from the server, like locations of our power plants and airplanes. However, some other layers only include data that we derived on the client, like the buffer geometry and the distance lines. We want to do these updates as efficient as possible and also make sure we're using the right layer type here for our client-side features. So let's take a look at the code. In order to trigger our custom client-side logic, we need to get access to the actual geometries of our planes, which are consumed by a stream layer. To do that, I'm registering a data received event handler on the stream layer view. And this event will fire whenever the layer view receives new data. So the code executed inside my event handler gets called for every location update for every airplane. Looking inside this function, we see that we have three major steps. We will go over each of these steps in detail, but first let's take a look at it from a high level. First, we're querying the nearby power plants, and this gives us the set of sites that are within the buffer distance as well as the buffer geometry. Next, we create the new lines, so the line between the plane and all the nearby power plants, update the lines layer, and then finally we create the new buffer polygon around our plane, which is then again used to update the buffer layer. Okay, so let's start with the first step, querying the nearby power plants. To execute the query, we're using the power plants layer, which is a regular server-side feature layer. We use that layer to create the query template, and then we add the set of properties like our geometry, which is the plane point, the distance, in our case, this is 50 kilometers, and a few more properties that I'm skipping here. We will then use the query to execute the operation on the power planes layer view. So this is really important because we're not executing a query on the actual layer, but instead of the layer view. And we're doing that because we want to make sure this query is executed in the client to get our results really fast. Next, we use the resulting set of sites to get the new polylines that are within the buffer distance. So here I'm mapping over these sites using the geometry to create a new polyline, which is just a path between our plane point and the point of our site. Next, I'm using the polyline here to first create a calculate a distance using the geometry engine, and then putting this distance together with the unit inside an attribute that gets then combined with the polyline geometry into a new graphic that is returned from this function. I'm also adding the plane ID as an attribute here to have a reference to the actual plane. Before we look into how we update the lines layer, let's take a look at actually how we construct the lines layer. We're using a client-side feature layer in this case because we want to make use of the labeling and also the querying capabilities of feature layers. Here I'm defining the label class, which uses an arcade expression to label our polylines with the distance that we have just added as an attribute to our polylines. Okay, so how does the actual update look like? First, we are querying the distance lines layer that we just created by using the plane ID. And we do that because we want to delete all the outlines for this particular plane. So as a result here, we get the set of previous plane lines for this particular plane ID. We will then call apply edits to do two things at the same time. One is to delete these old features, and also we are doing this to add new features, in this case our new polylines here. So this can be done in just one step. Next, we are updating the buffer graphics. When I call get new buffer, I'm passing in the buffer geometry and also the warning boolean, which tells me if the buffer symbology color should be green or orange. I'm also passing in the plane ID, and this is then used here to create a new graphic. The geometry is just the buffer geometry that we received from the initial query nearby operation. For the attributes, we're adding the plane ID, again, to have a unique reference to this particular graphic. And then, as a last step, we're adding the symbol, which is either a green circle or an orange circle based on the warning boolean. Our last step for this example is updating the buffer layer. The buffer layer is just a simple graphics layer because here we don't need any querying, labeling, or rendering capabilities. And that also means we can use the collection functions to simply update the collection of this buffer layer. So first, I want to remove all the old buffers. So that should be always one buffer with the plane ID. And that means I'm using a filter function to identify the existing buffers for this plane, and then passing in the result of this filter function into the remove many function. The second step is just simply adding the new buffer. And that is already everything that is required to update our client-side features on the map. Like I said before, these steps are executed with every change in the plane stream layer. And therefore, it is important that we perform all these queries within the client to make sure our updates are fast. I hope this demo gives you an idea of which client-side capabilities you can use with your real-time data in your applications to create new insights and visually appealing maps. For our next example, we are looking at simulated bus positions in Charlotte. Similar to most tracking data, we're getting constantly updates about the locations of our assets. For buses, that could mean we have simple point graphics that are getting replaced as soon as we receive an update for this particular bus. However, this does not always represent how our assets move in reality. Instead of getting distinct updates, we might want to visualize our assets as something more continuous that allows our eyes to follow the movement easier and better understand the speed and direction into which our buses move. My second layer here tries to address this problem by visualizing our bus trajectories as animated lines. As you can see, these lines slowly progress towards the next observation and fade out towards their tail to indicate the direction. Although this track animation does not reflect the real size of our buses, it might still be helpful to better detect changes from a quick glance at this map. However, there are some limitations with this new layer. For example, it only works well with datasets that provide accurate location. As soon as we have gaps in our trajectories, or the recorded locations are jumping around, this animation might be misleading because it would show a wrong trajectory, and in these cases, it might actually be better to just show single points as we did with the previous layer. The effect that we see here on the map has been achieved with a custom layer view implementation. For this scenario, I extended the base layer view GL2D class that exposes WebGL rendering capabilities and allows me to implement multiple functions of the layer view lifecycle. First, the attach method is called when the layer view is about to start drawing the layer's content. It is usually responsible for resource allocation. Then, during the lifecycle of the layer view, the render method is called once per frame. It must complete drawing before it returns. Finally, the detach method is called after the layer is removed from the map, and it releases all allocated resources and stops ongoing requests. Each of these functions has access to the map view's WebGL context. The developer must provide its own shaders, meshes, and textures, and is responsible for setting the required GL states on the context. In this session, I will not go into the details of how we could implement this custom layer view with WebGL. However, if you want to learn more about these concepts, I highly recommend taking a look at the animated lines with WebGL sample on the API docs. This sample demonstrates how to implement the same effect for polyline graphics. In fact, most of my code is taken from this sample and adapted for stream layers. Below this API sample, you also find detailed descriptions of the underlying concepts. In my last example here, we are taking the previous approach one step further. Similar to the custom layer view in 2D, we can also register external renderers to provide custom views for 3D content in a scene view. What you see here is the air traffic over Western Europe, visualized as animated lines that also indicate the elevation for each flight. For this demo, I'm using a dataset that simulates the movement at a faster speed, and I also increase the elevation to highlight the offset to the ground. Similar to the last example, this visualization can be helpful because it indicates direction and speed much better than single point geometries, for example. And this is especially true for assets that seem to be moving slowly because we're looking at it from very far away, as in this scenario. At the same time, these lines, of course, do not represent the actual size of our assets and could be misleading for certain use cases. For this demo, I'm receiving data from a WebSocket and passing it into the external renderers interface of the JS API. This interface offers me low-level access to the scene view's WebGL context and allows creating custom visualizations that interact with the scene view the same way as built-in layers. Developers can either write WebGL code directly or integrate with third-party WebGL libraries. Because working with 3D environment gets very complex, I decided to use Three.js for rendering my plane trajectories on the map. Three.js, in contrast, is a high-level library that takes away a lot of the effort that is usually required when developing a standalone application or plugin. Again, we will not go into details for writing external renderers in this session, but I highly recommend reading the information on the corresponding API module. This gives you all you need to get started, including how to request redraws, which is very important when working with real-time data. Going back to our example, I will instead focus on the three main things that we have to consider for using real-time data. First, it is very important that your renderer is time-aware. Because our geometries are getting constantly updated, we need to make sure only the relevant part is shown to the user. In my prototype here, I'm handling down information about the currently visible time frame to the material of my custom mesh. By doing this, I can decide what needs to be rendered inside the WebGL shaders, which is more efficient and allows me to apply custom effects like the fadeout that we see towards the tail of our animated line. Second, we need to constantly update our renderer and make sure we synchronize the visible time frame. This usually requires requesting a new renderer call after we finish an update. And finally, we also need to update our geometries whenever we receive new data and make sure that we also remove obsolete geometries that are no longer visible to the user. The details for this process depend a lot on your data and use case. In my demo here, I'm just making sure we are removing any observations that are older than 30 seconds. Keep in mind that all these additional steps are only required if you're implementing your own external renderer. For many scenarios, it is sufficient to use one of the built-in layer types of the API, which can be used out of the box. I hope this gives you an idea of what is possible with real-time data and the custom visualization capabilities of the JS API. And now, I will hand it over to Matt.
Thanks, guys. I'm Matt George, a rendering engineer on the JavaScript team, and I'm going to talk a little bit about some of the more recent updates to Streamlayers in the 4x JavaScript API. To start us off, one of the more major changes to Streamlayers recently has been the introduction of our unified feature processing pipeline. With this change, we've unified all feature and stream layer rendering. That means that all feature source types are now treated as streams, and all feature and stream data goes through the same simple processing pipeline. While most of this is an internal implementation detail, it does have some impact for users. Importantly, what it means is that all of the feature layer APIs are now available in Streamlayers as well. This includes all of our variety of renders, sim support, feature filter and feature effects, our dynamic attribute-driven filtering APIs, and client-side queries as well. As you've seen already in this presentation, we're excited to see what kind of dynamic visualizations users will be able to build with these new APIs. Another change is the new auto reconnection logic that's now built into every stream layer by default. Versus 3x, developers no longer need to re-implement the same connection logic just to reconnect to WebSocket when a connection is lost. And this means that WebSocket handling is now fully automated. When a connection is lost, the API will automatically attempt to reconnect. And developers can customize this behavior with the new max reconnection attempts and max reconnection interval options that were added in 4.17. Stability and performance is an area we've really focused on with the 4x API. Historically, it's been very difficult for developers to dial in the right push rate to handle a variety of clients. And this is because there's a pretty big difference between a mobile client and a desktop client. A low-power mobile client may only be able to handle a tiny fraction of the updates per second that a more powerful and power-intensive desktop application can. To handle this, we've overhauled stream processing in 4.17 to properly handle back pressure. Stream feature processing will now automatically throttle for slow clients and will attempt to drop obsolete messages first. This means that if a given track ID receives multiple observations in the time that it's only been able to process one, it'll drop all but the most recent in order to avoid rendering stale data and overflowing queues. We wanted to make this new behavior transparent, so we added the new update rate event to enable users to see what the client and server update rates actually are. Developers can use this new functionality to expose the update rate to end users or to send reports to some backend to diagnose network problems. We've also added the new update interval property to give developers more flexibility in setting the maximum client update speed. Use this property to set a maximum client update speed that clients will not exceed. Under the hood, we've also made a variety of tweaks to optimize how fast we can push stream features. As our demand for real-time and IoT data increases, we want to make sure that the stream layer can continue to support ever-increasing demands for higher update rates. And as part of this, in 4.19, a new stream layer-specific patching routine has been added. As part of this, stream layer should now be able to support a higher number of updates per second, and users should notice improved frame rates for existing services. The last major change has been the introduction of custom stream layer support. This functionality was added in 4.17 for 2D and 4.18 for 3D. And what custom stream layers do is they allow developers to set up their own backends to push streaming data directly to the API. To make these work, developers must provide an implementation that supports projection, server-side filtering, and other logic required by clients. So there's definitely quite a bit more work here than just getting started with Velocity or GeoEvent, but we hope this will help to solve some of the advanced integration use cases that users have had in the past, as well as make it easier and provide an official way for adding custom services to the API. Going into a little bit more detail about the protocol that's needed here, the major difference of these custom stream services versus the stream service specification that's pushed out by Velocity and GeoEvent is fundamentally that there's no metadata document here. So, with the stream services, typically right there would be a REST endpoint, and that REST endpoint you could reach to get some metadata about the service. But to make it easier for developers to set up their own custom stream services, we've opted for a handshake approach here instead. And the structure of the handshake looks something like this. So there is a format to return the features in. At the moment, currently only JSON is supported, and that'll be served over WebSocket text frames, though we're looking to extend support in the future for other format types. There's a spatial reference to return the features in, and finally a list of outfields or attributes to include in each feature sent over the WebSocket connection. One thing you'll notice here is that geometry filter expressions are currently not supported for custom stream layers, but that's something we may look at adding in the future. An important thing to note here is that any valid stream service is going to need to implement all of this functionality. However, if you control both the client and the server, you may be able to get around this in certain scenarios. For instance, if you know that the client and the server have their data stored in the same projection, you may not need to implement any kind of reprojection logic yourself. After we've completed the handshake, the second part of the protocol relates to the feature messages themselves. Feature messages need to use the following format. So you'll specify the type as feature result, and then you just include a list of features. The reason why this type information is necessary is so that we can support additional messages in the future. And just sort of an implementation tip here, batch updates is really going to be the way to go. So definitely take advantage of the fact that features is an array here, and you're going to want to push as many updates as you can in a single message, up to some fixed size, of course. But we do feel that it's going to be more efficient to push arrays of features rather than individual ones. And to wrap up custom stream services, let's take a look at a quick demo to show how you might be able to use these. So as this loads, let me take a moment to go over what we have here. What you're looking at is a synthetic stream service showing generated cars in New York City that we've created with a network graph of polylines taken from New York City open data. This data is great because it contains all the road segments in New York City and the nodes that connect them. I've also pushed those polylines to a hosted feature service that I'm displaying along with the points in red. And using that, we're basically just moving randomized points along those polylines, selecting a random adjacent segment when we reach an intersection. And as you can see here, I really do mean all of the polylines. But the point of this is just to show a benchmark that we use internally for evaluating Streamlayer performance. And what we can see here is that we have around 200,000 moving synthetic cars that we're then pushing from the service at a rate of around 80,000 to 100,000 updates per second that we're then able to handle on the client at a bit lower 75 to 80,000 update per second rate. And if we go ahead and look at how this is set up here, we can see that it's pretty easy to connect to a custom WebSocket service. So the main thing, right, is the introduction of this new property. So you're going to specify the WebSocket URL of the WebSocket that you want to connect to. Here, I'm just using something hosted locally. And then you're going to need to specify the required metadata. So as we mentioned, right, there's no JSON endpoint here. So you need to specify this in the layer itself. So in this case, at a bare minimum, you're going to need these two fields, the object ID field and the track ID field. You're going to need to specify what the geometry type is. Here it's points. And lastly, you'll just need to map the fields you already specified to what they actually are. So object ID to object ID field and track ID to track ID field. And with that, we've done everything we need to connect to our custom stream service. And to wrap up, I just wanted to touch on some of the things we're thinking about adding in the future. The first of these being a kind of higher level client-side stream layer. And the motivation for adding something like this is that it would help to solve this sort of last remaining set of integration challenges where developers might not necessarily have access to a service that they want to integrate with, or for various reasons, they don't want to create sort of this custom server-side proxy in order to feed the data API. For those sort of challenges, using a client-side stream layer would allow developers to leverage a lot of the functionality that's already within the API for doing stuff like client-side projection. And it would allow for developers to push really arbitrary data to the stream layer. And so if there are some advanced business rules that need to be built into the logic for how exactly you display features, this would help to cover those use cases, as well as help with testing and things like that for a pure a client-side type of approach here. And we also think that it would help to solve a variety of use cases we've seen crop up lately where developers create graphics layers and push a lot of graphics, various things based off of how exactly they want to move features because they need that fine-grained control. Using a stream layer to do this instead would be a much more efficient thing for us to do and support on the API side. And so, this would be a much more performant alternative to that existing workflow. The other thing that we want to continue to look at is supporting more advanced visualization options. And I think the biggest thing that we're still missing here in 4X is the track renderer. It's great to be able to visualize the last point, but when you want to visualize a trail of points, that functionality is not yet in the API. So, providing a way for, really customizing how exactly the look and feel of those tracks are visualized, we think that that's something that we still need to work on. And a track render is going to go a long way in supporting those use cases. And of course, we want to know what you guys would like to see and what you guys are looking forward to. So be sure to let us know. We can always be reached on GeoNet and GitHub. And just really quick, I wanted to plug for another session with our lead WebGL developer, Yaron, and my colleague, Dario. Basically, if you're interested in building more advanced custom stream layer visualizations, definitely check this out. It's a bit more of a technical session, so it does require some knowledge of WebGL. But they do show how if you're willing to put in the work to do the WebGL visualization yourself, you can really tailor things to your specific use case and create a really responsive application. And we've reached the end of the presentation. So, thanks everyone for watching. And hopefully next year COVID will be over and we'll be in person. Before you go, please make sure that you provide feedback for this session by clicking on the session survey link directly below the video. We definitely use that feedback and we want to know how we did. So be sure to click on that. Again, thanks for watching, everyone, and be sure to click that feedback button.
And now we'd like to open it up for the Q&A part of the session.
Hi, everyone. I'm Jan Kevin. I'm working on the JavaScript API team, and I've been moderating this session with these three amazing presenters, Julie, René, and Matt. We have received a lot of questions during during the session, and of course we'll try to answer them as much as possible. So the first one is gonna be for René. When would I want to use GeoEvent Server versus Velocity?
Yeah, sure. So when you compare both products, the functionality of both products, they're actually very similar. So they both provide full end-to-end solutions to ingest, analyze, but also visualize your data, your real-time data. So it really comes down in the end to what deployment options you want to consider. So GeoEvent is more like a traditional software product. Like I said in the presentation, it is installed as part of ArcGIS Enterprise in your own infrastructure. And in contrast, ArcGIS Velocity is a capability of ArcGIS Online. So it is provided as a platform that is fully managed by Esri. And because of that, you don't need a GIS admin to manage it.
Thanks, René. Our second question is about removing features using the WebSocket. Can WebSocket stream support remove operation? It currently supports add and update only, but however, in some cases, some vehicle, for example, is no longer in service. And we would like to see the feature removed from the map. You have some info about this, Matt?
Yeah, great question. So unfortunately, at the moment, stream services don't support remove operations. So if you want to remove stream features, what you will have to do is set up a purge option. So right now there's a variety of purge options where you can display the last point of a track. You can remove points after some period of time. It's definitely something that is interesting to us, and we'd like to further build on stream layers and stream services and extend support for this. If you do need remove, probably you would have to go with a more sort of client-side approach where you listen to the WebSocket directly and add and remove things from graphics layers. This will work if you don't have many graphics, but performance may be an issue. So definitely in the future, it's something that we'll look at improving.
Thanks, Matt. I will post the link to the purge option property in the chat. René, could you provide more details or documentation on publishing stream layers?
Yeah, sure. So both products, GeoEvent and also Velocity, are able to output data as stream layers. So you can go into both products and publish your own stream layer. And I will post the links here to the documentation of both products.
All right. Thank you. So we have another question about what are the layers of the JavaScript API that are better suited for real-time data. Currently, we listen for data changes on WebSocket and then apply those changes on the feature layers. Matt?
Yeah, sure. So stream layers are definitely going to be the way to go here. For your specific use case, if the problem was that you had a WebSocket connection and you weren't able to directly feed that to anything in the past, the custom WebSocket support that we added, I think in 4.17, right, should help to cover that use case. You'll have to write an adapter to fit it in the message format that the custom stream service expects. But if you use a custom stream service, I think that should provide much better performance.
Cool, thank you. I think, Matt, you created an example project to demo the stream service. I'm gonna send that over. It's in the description. In the description of the stream layer class on the API reference, but I post also the link.
Yeah.
Okay. René, there is a question for you: how to use stream layers with MQTT platforms?
Yeah, that is a good question. So again, Velocity, but also GeoEvent are able to consume data from MQTT platforms. So for GeoEvents, what you have to look for are input connectors, and that is something that is provided out of the box with both GeoEvent and Velocity. And yeah, we'll also go ahead and post the links here to the product documentations.
Well, another question for you. StreamLayer is supported by GeoEvent or ArcGIS for Server or ArcGIS Online?
Yeah, so I think, like I said in the other StreamLayer question, so GeoEvent and both Velocity can be used to publish stream layers, to consume any other data, and then perform analysis and output these results as stream layers that can be then consumed by the ArcGIS API, for example. But of course, you can also work with other products like ArcGIS Online and ArcGIS Pro to consume stream layer data and work with this data.
Thank you, René. So Julie, will we be able to access the video later?
Yeah, actually, I just found out that it should be posted 2 to 3 hours from now, or from the end of the session. So sometime today, I think, actually.
Yeah, it's very late, very fast.
Yeah.
So I think we have the same very similar question as before. Do we have a documentation that explains how to generate fake stream data? We don't have like a documentation on the message format, but you can find inside the StreamLayer API reference, there is a link to the same to a GitHub repo that shows you how to create a fake stream service using Node, but you can apply the same technique using a different technology server side. How can I use stream layers in the beta map viewer? And more specifically, do we have access to settings like breadcrumb trail? Matt, can you answer this one?
Yeah, sure. So unfortunately, at the moment, the map viewer beta doesn't quite have full stream layer support yet. So it'll be able to, you're able to view and open a stream layer, a web map with a stream layer in it, but you're not able to author them or to configure them. That's something that is being worked on and will be coming soon, but you know, we don't quite yet have a timeline for that yet. As for the breadcrumb trail, that's something I sort of touched on in that last slide that I had. To implement this, we really need to have support for the track renderer. In terms of the timetable for that, we're still in sort of the planning stage, but you know, we're hoping that it's within a year, we can at least start working on rolling out beta support for that.
Nice, thank you. Julie, another question for you. Is there a way to measure buffer distance from a boundary instead of a point?
Yeah, I'm gonna try to share my screen. Hopefully it's being displayed. So there's actually samples in the documentation for how you can buffer a polygon. I think that's what's being asked, a polygon instead of a point. So this is one example that's just showing how to apply effects, but it's kind of doing the same thing. So you can see the inner square, and then I changed that. It's changing the buffer distance and then doing that intersect with the polygons around it. This one's doing something similar, only it's 3D, so I can draw a polygon and then adjust the buffer distance. So yeah, it's not limited to points.
Nice, thank you, Julie. Another question about how to learn WebGL. Are there any plans to have WebGL rendering implemented in other service in the ArcGIS stack, or other ways to represent animated data? So the JavaScript API uses WebGL to render the entire map. So all the layer types are using WebGL. There are samples. I will look it up in the API reference to learn how to build custom WebGL visualization. using WebGL, it's I don't know how to use WebGL. So there is quite a steep learning curve there. But we have samples that shows how to do animation and using WebGL. We are also, it's long term. There is no time frame for this, but yeah, we are interested into bringing more animation capabilities on vector data. But yeah, for now, we don't have that. So I will try to post a link to the resources we have in the API reference about that. René, we have a question for you. Is there documentation to publish a stream layer for Velocity? And also what type of license Velocity supports?
Yeah, so stream layer outputs are one of many output types that are supported within Velocity, and I will post a link to documentation here in a second. Regarding the license types, there are 3 different license levels right now, and they're all based on the velocity and also the storage that depend on your organization. And I can also post a link to that site right now.
I think we have another question that is kind of related. Can I publish stream layer on the new ArcGIS platform?
So that's like hosted stream layers. That would be Velocity, right, René?
Yeah, right. That's actually very similar to the previous question. So yeah, that works with both products. Actually, with Velocity, it will be available inside your ArcGIS Online organization.
There's a question, what kinds of services are supported? And that was a really early question, so maybe that person learned during the session, but essentially it's stream services, or as Matt covered, the custom WebSocket type as well. In terms of what Matt presented for setting that up, it's all in the documentation for what's required for the service that you're going to be consuming in the stream layer in the custom case. So you can use that as a reference as well.
And yes, I think the link to the presentation, the slides will be shared at some point. So you can also join us on the ask our experts chats and ask questions. One person of the team will either answer to you directly or ask us, and so we can provide the best reply for you guys. And
there's a question, where are these shared links? So all the links we've been sharing are replies to the questions. Hopefully you guys can see that. I'm not sure how you get to it from a participant, but that's where we shared it. If you're unable to find them, then just find us at the Ask the Experts. We'll get them to you. All right, everybody, thank you so much for joining us, and look forward to seeing you in our next session.
Thank you.
Bye.
Guys.